Hello everyone, welcome to the next lecture on the numerical analysis. Today we will discuss about condition number which is related to the matrix No. Myself Dr. Harish Garg. You can simply follow my YouTube channel where you can find the various lecture on the numerical analysis. So as we have discussed and we all know how you can solve the system of the equation Ax is equal to B. There are several methods. First of all, you have know about that you can solve this by using the direct method. But how you can solve this system when you are trying to move on the numerically, then which are categorized into the one is called as the direct method, second is called as the iterative method, and this method is also called as indirect method, and which are the classification of here. But before solving this solution of this system, we must know about that there exist many linear system Ax is B whose solutions are not stable. What is the meaning of that? If you simply perturb the values in B or in the value of A or in the both, then we will not get a stable solution. For example, if I consider this system, then you all know how you can solve this system of the equation. You can simply find the inverse of the matrix A. This is my A. You can find the inverse of the matrix A and then multiply this by B. You will get the solution as here. Fine, that's a very simple problem for you. Now, if I simply perturb this right hand side vector like here, you can see I simply change 32 to the 32.1, 23 to the 22.9. There is a plus minus 1.1 difference between them. You can also see 32.1 you can round off them to the 32. You can round off them to be the 32, or 22.9 is you can round off them to be the 23. Similarly, 33.1 you can round off them to be the 33, and 30.9 you can round off them to be 31. So, but can you make the round off as easy as look like say this one? So you can see if I simply perturb the right hand side and if you find the solution of this problem, then you will get the right answer as here. And you can see which is very far away from the original solution. So what is the meaning of that? If you simply round off these numbers to the original linear system, then the solution is very far away from the original one. On the other hand, if I simply truncate or I can simply perturb the matrix like of this, you can see I can simply change this number to 8 to the 8.1, 7 to be the 7.2, 5 to be the 5.04, and so on. Clearly says this matrix is again becomes A when you round off them to be the certain accuracy, like 4.99 is becomes a 5, 6.99 becomes a 7, 5.98 becomes a 6, 9.98 becomes a 10, and so on. All these numbers are converted into the original sequence, and here I can preserve the B as a fixed number. Then if you find the solution of again by using the axis A inverse B, again you will be analyzed the solution is very far away from this original one, 1, 1, 1. You can see there is a very far away from the solution. So what is the meaning of that? A small change in the data either in the form of the B or in the form of the A will change the result drastically. Fine. So what is the meaning of that? You can't truncate or you can't round off them to any number unless you will get some desired accuracy. So what is the meaning of that? It means the system of the equation is very sensitive to the round off error. Like as I defined you in the two example, you can simply round off them. It is approximately to be the same system, but it is a very sensitive to the solution, as you can see from these cases. So what is the meaning of that? So it means we can get a different solution when you get a rounding off to the desired or the different number of the decimal digits. So why this happening? The question arises is why this happening. So this problem is occurring in the matrix because of the Bagley condition. What is the meaning of the Bagley conditions? So this Bagley condition is basically categorized into the two category. One is called as the ill condition and second is called as the well condition. When you can say any of the matrix A or system Ax is equal to B is said to be the ill condition or the well condition. So for that we need some results. So what is that result is? So if I look at again these two examples, here I change the value of the B only. So in all these cases, whether you can change the B or you can change the A as I discussed earlier. All these cases will leads to the ill condition. What is the meaning of the ill condition? When you get a drastic change, in the solution, then the system is called as the ill condition. And you can see, if I consider simply change in the B, and you can see the solutions are drastically changed. On the other hand, if you get a solution like of this 1.01, 1.2, 1.0 and 0.99, you can see it's a very less change in the solution. Then we can say the solution is my well condition, or the system is called as the well condition. Now what is the meaning of the ill condition? How you can measure them? Because it's not an always easy you can solve the system by the perturbation, but how you can measure the illness condition? The measure of the illness condition is given by this condition number, and that's the lecture of this today's topic. So that's what is the use of the condition number is it can measure how much the strength of the ill condition in the system of the equation. Now in order to understand this condition, let us explain in detail this concept of ill condition. So as we have a system of the Ax is equal to B, we can get a solution only when A is my invertible matrix. That means determinant of A must be non-zero, or you can say A inverse exists. Then as I told you, there are two kind of the changes which we can get a solution. Either we can change the right hand side, that is a B to the B plus small change, and A to the small of delta A. So let's firstly discuss the case 1. So if you have the two system, one is the Ax is equal to B, original system, and second is when you change the B to the B plus delta B, the solution will be changed from X to X plus delta X. Fine. Then on the other hand, if I change the matrix A to the A plus delta B and keeping the B value as a preserve, then the system will be changed from the X plus delta X. Then we can find what will be the error bound, what is the maximum change in the error we can observe. Then the following inequality holds in the case 1. What is that delta X? This is nothing but my relative error. Fine. This is nothing but my relative error of X. This is the relative error of the B. On the other hand, if I change the matrix A, then we can get the solution in this form. But how we can correlate with them? So let's see, explain in the detail one. So see, first case, I can prove this result in this couple of slides so that you can easily understand the result. So let's say if I change the matrix B to the B plus delta B. Fine. So now if I see, you can see this number is nothing but my X plus delta X. Fine. This number is my B plus small change in the B. So now if I open this bracket, what will happen? This becomes my A, because you can open them. Now A is equal to Ax is equal to B, so it will be cancelled out. So this number becomes my A, small change in the X is small change in the B. Because A is my invertible, so you can find the A inverse of here. Then you can take any of the norm as per on your convenience. You can take as norm is as max norm, this is called as the max norm, or it is also called as the maximum row sum norm. Fine, that's on your choice. So this is by taking the norm on this. So what is the meaning of that? Norm of B is norm of A into X. So we all know what is the property of the norm of AB, which is less than or equal to norm of A, norm of B. So I can use this property here. It is a norm of A into norm of B. So I can written like here from this. Same, I can apply the norm definition here. You will get this result. Why? Because you can see norm of delta X is from this case, which is equal to norm of this one. Fine. Then I can use this property, product of the norm must be less than or equal to norm of this one. Then what you can do, you can find the value of the norm of X from here. What is the norm of the X from this? It will be less than or equal to this one. Then I can see this is equation number 1, this is equation number 2. I can multiply this equation number 1 and equation number 2. You will get this is the required expression. What is that? This is the relative error in X, this is the relative error in the B, and this is the case of the, this is a bound, this is a bound of relative error. Fine. When you small change in the, when you perturb the right hand side vector. Case second, when you perturb the A matrix to be the A plus, like here you can simply change 8 to be the 8 plus 1, 6 to be the 5.98 and so on. So this value, this matrix is called as A plus delta A, this is my X plus delta X, and B is my same, so I call as a B. Again I can open this bracket, it is my AX plus A delta X plus so on, so you will get this expression. Again AX will be cancelled out, so I can return like here. A is my invertible matrix, so I can find the value of here. Again you can take the norm on the both side, the first expression becomes my here by using this property. Now I can take the norm on this second side, so this is norm of A is norm of minus A inverse of X plus delta X of delta A. Now I can use this property. What is the alpha? Here alpha is my minus 1, so what is the mode of alpha? In this case it is my plus 1. Then in this case I use this property, which is nothing but less than or equal to here. Again I can find the value of this, or I can find this number, I can take X on the left hand side, which comes to be here. So again from 1 and 2 you can easily derive this equation. That's again, this is the error bound on this equation. What is the meaning of that? It means if we simply take delta of A, that is changes in the matrix A is very very small, then it is not reasonable or unreasonable to expect that this ratio is also closer to the relative error. You can't say that. So what is the conclusion of that? So we can see there are the two different bounds on the system of the equations. So from this system bounds we can see, when you perturb the two systems, we can see the relative error is bounded by the relative error of this. This is the relative error change in the A, this is the relative error change in the B. So which is bounded by the relative error in the information multiplied by this number. You can see that both the numbers are same, and this result will motivate us to define the number called as the condition. What is that? Basically condition number is this number, which is a common to the both side, is called as the condition. So if you have the invertible matrix A and the matrix norm, any of the matrix norm here, then this quantity is called as the condition number with respect to the relative norm. This condition number is also denoted by K of A. We can write like here. What is that? If K of A is large, what is that? It means if condition number is large, it means the product of them is a large number. So the condition number is large means when you small change in the matrix A or small change in the vector B, then it will produce a very large change in the system here. That means the condition is ill condition. On the other hand, when when the condition number is approximately same or approximately 1, or it will be the less than 1, then you can say the condition is well condition, or system is called as the well condition. What are the different form of the condition number? Based on the different norm of the different norm, because this is my norm, it can be the norm of infinity or max norm, it can be of the spectral norm, it can be of norm of 1, and many more are there. So if I consider the spectral norm, that means it is on the L2 norm, fine, or it is also called as Euclidean norm, fine. Then how you can find the norm of this? So you can write like here, and as we already discussed the vector norms in our previous lectures, which is quantity here, where lambda and mu are the largest and the smallest eigenvalue in the modulus of A star of A. But if your matrix A is Hermitian or the real or the symmetric, then we all know A and the A star are same, then we can say this number is nothing but my A square. So the eigenvalue is nothing but my only lambda over mu, where largest and the smallest eigenvalue of this. Why? Because if I simply take this is the lambda square and this is, then square will be cancelled out, we will get the same expression. So what is the condition number? Is that it measures how the sensitivity of the system AX is equal to B, meaning or house sensitivity with respect to the variation of the B and A. So we can say the condition number is large. Whenever the condition number is large, the system is a ill condition. Whenever the condition number is a very small number, then we can say it's a well condition. For example, how you can find the condition number of the matrix? By using the absolute sum row. That means you are using this one. This is a norm. So what is the definition of the condition number is? You have to here. So for that you need to be the max norm. So how you can find of this? By the definition of this, you can take the absolute value of this row sum. So this is the first row, fine, comma, you can find the absolute sum of this second, 9 plus 16, comma, and so on for this third one. So the absolute sum of the first row is my 14, absolute sum of the second row is my 29, and so on. So maximum value is my 50. In order to find the absolute sum of the A inverse, we firstly find the A inverse. We have the matrix A, you can find the inverse of this. Then what is the norm of the A inverse? Maximum absolute row of this. So what is the meaning of that? It will be plus 31 over 8. It's a minus, but we take the absolute values, is plus 44 by 8 plus 17 by 8, fine, comma. Similarly, you can take the second row, it's a 44 by 8 plus 56 by 8, and so on. You will get as these are the sums. Means if you take the sum of the first row, it is 92 by 8. If you take the sum of second, it's a 115. It's a 44 by 8. Then the maximum value will be 50. Substitute both the values at here, you will get this number as here. Now clearly say this number is very large number, so it means that this system is my ill condition. So if you small change in the any of the number, it will give you a very drastic change in the solution. Look at the another one. Fine. Again we have considered same example here, but now we are using the spectral norm. That means we are taking the L2 norm. It is also called as the Euclidean norm. So as the matrix is real and symmetric, that means if A is equal to A star, or you can see A is equal to A transpose, then the condition number is nothing but lambda over mu, where mu and lambda are the minimum and the maximum eigenvalue. How you can find the eigenvalue? I can start from here. We can find this value where I is my 3 cross 3 matrix. You can expand this determinant, you can get this equation. So you can use your calculator, you can find the cubic equation roots, which comes to be here, or you can find the roots by using the bisection method, by using the regular falsy method, secant method, fixed point method, Newton-Raphson method, or any other. Now from this case, can you find the value of what is the maximum absolute value? This is my maximum value. And what is the minimum absolute value? What is the minimum value is my here in terms of the modulus. So this is my mu, this is my lambda, so I can substitute here, you will get as the condition number this. So clearly say this is again a very large number, so we can say this is again a ill condition problem. Look at this one. So you can see this is, if you round off them to the 1, then the determinant will be 0. So we can see whether it's a ill condition or not. So since the norm is not given to you, so I can simply consider it as a infinity. So what is the norm of infinity? So we can take the maximum value of absolute sum of the first row, absolute sum of the second row, fine. So what is the maximum value is 3.001. For finding the A inverse, we can find the A inverse, and then we can take the A inverse of this, take the absolute sum of this. So the absolute sum will be my 20,000 and the absolute sum will be 10,000.5. What is the maximum of this? It's my 20,000 is here, fine. Now you can substitute both the values at here, you will get as 60,000 of 2. Clearly say that which is a very large number, so it means small change in the value of the A will give you a drastic effect on the solution. Look at this one. Find the condition of the matrix A and then check whether and check when the matrix A is said to be the ill condition. So again we are using the same definition. What is the norm of A? Infinity. So we can take the maximum of 1 plus mod of C and mod of C plus 1. So which one is the maximum? Since both are same, so the maximum value will be same. You can find the A inverse, which comes to be here. Then what is the A inverse of this? It will be the maximum of, the first value will be 1 over 1 minus c square norm plus mod of c divided by 1 minus c square, comma. Similarly for the second, you can get as here. Now you can see again both the numbers are same. So what is that? I can written as a minus of mod c as a plus of here. Now I can substitute both value here. What is that? This value becomes my square, is my condition number. Now when it will be the ill condition? Ill condition means your condition number will be very large or it will be greater than 1. So when it will be the large number, you can see when you take c either as a 1 or you can take c is my minus 1. In both the cases, your condition number becomes my infinite, that is a very large number. So you can see the possible value of the c is when you take c is either exactly 1 or the mod of c is approximately to be the 1, then the condition becomes my ill condition. Look at the another example. If you have the matrix A which are depending upon the parameter alpha, you have to find the alpha so that condition number will be minimized, and we are using the max norm. So this is the definition of the max norm by taking the infinity. Okay, so you have the A, you can find the A inverse, find the max of A inverse, so that is the sum of this. So what is that of A of infinity? Maximum of sum of this value, so it is a 0.2 of this number, and the sum of this will be my 2.5. Fine. So you can't say that this number is greater than, because it depending upon the alpha. So yours, by using the max norm, it will be here, and similarly for this case you will get as this number. Now when it will be the minimum, so I can substitute both the values in this equation. You will get, or you can see from here, this number will definitely be a maximum because each quantity has a similar. Now I can substitute equation number 1 and equation number 2 in this equation. Fine. Then your target is to prove this will be the minimum. How you can prove? Because I can simply firstly multiply this quantity inside. So I can return this number as max of, I can multiply 0.2 alpha of this. Alpha will be cancelled. So it is my 0.4 of this plus it will be, when you multiply this, it will be my point, it will be my, it's a 10, it's a 6, comma. Then I can multiply 2.5 with this quantity, you will get as this expression. Fine. Now when it will be minimum, the question arises is for what value of the alpha you can choose so that this will be minimum. So this will be minimum only because we all knows that if I say this is my x, this is my y, when it will be minimum? When x is equal to y, because whenever x is less than y, then you can say the minimum is my x, but when you take x is greater than y, the minimum will be y. So this will be minimum only when both the numbers are my same. So can you find the value of the alpha from here? You can simplify this and you will get the alpha as here. Then I can substitute this value of the alpha in here and you can take this maximum, you will get the right answer as 11. Now the last result is, what is the upper bound of the relative error? What is the meaning of that? If you have the invertible matrix A, x star is my approximate solution of this, r is my residual, then the maximum norm of this is my here. Or you can say if x is my non-zero, then this quantity, what is that? This quantity is called as my relative error. Fine. The previous two results which I have explained, that this is the relative change with respect to change in the B or a relative change with respect to the A, but here this is a relative error with respect to the residual. What is the meaning of the residual is error. Fine. So look at that. What is the meaning of the residual is, if you have the system Ax is equal to B, if I know x star is my approximate solution, that means B minus Ax is my error or called as the residual. I can substitute the value of the B, this is A, so I can take matrix A as a common, so it will be x minus x dash. Then we need as a norm of this, so we can define as A is invertible because it is given, so I can found as here. Then I can target is to firstly prove this result. So take the norm on both sides. Fine. How you can solve that? So it will be less than of norm of this and norm of this. By using the vector norm property, norm of this is less than of norm of A, norm of B, and that's the quite proof of this result. Fine. Then how you can prove this one? This is already similar. I can take the norm of this vector. So what is the norm of this vector? Is a norm of B is equal to norm of AX, and norm of AX I can written as here. So from this I can find the value of this. So I can multiply the equation number 2 and equation number 1. You will get the simple maximum bound of this here. What is the significance of this norm? We can see the counter example. If I say X star is my approximate solution of this system, you can find the bound on the relative error. What is that? Firstly, you can start with the residue, because we need this. So I need to find the norm of R. I need to find the norm of B. Norm of B you can easily find that. So what is the norm of B? Maximum value of this 9.7. Fine. Can you find the norm of X star? We don't need the norm of X star. We firstly find the value of X. So we can start with the residue. B we have, A we have, we can have a X star. So you can substitute this value as here. So what is the norm of R? You can take the maximum value of the absolute. So the absolute value is my 0.0820 and 0.1540. So this value will be my 0.1540. Fine. So this number we have already computed. Norm of B we already computed from here. Norm of B is my absolute value in the row sum. That's a 9.7. Then we have to find the norm of the A. What is the norm of the A over the L over the max norm? You can take the row sum as a maximum. So determinant of A is non-zero, A inverse is. Now define of this. Maximum of 3.9 plus 1.6, and the second is 6.8 plus 2.9. So the maximum value of this becomes my 9.7. Similarly from here I can take the absolute sum of this plus this, absolute sum of this. So it becomes my 24 point something. So it is my here. Now I can substitute all these values in my this equation. You will get as here. So after the calculation you will get as this one. So it means if you consider this system, the maximum error bound in the relative, maximum bound on the relative is my 3.832. So this is the way you can learn about the concept of the condition number. So based on this condition number, we will try to explain you in the next lecture as the Gauss elimination methods and the other lectures as well. Till then you can simply like, share and comments on my video. Best of luck students. Happy learning.